purpose of this video lecture is to introduce you to chemistry as a branch of science, the study of matter, and the way in which we study matter, which is using the scientific method. What is science? It is a process used to learn about the world. It is systematic and it involves observations, experiments, and data. So this is a simple graphic showing the steps of the scientific method, and I'm going to go through this using an example from my very first job outside of college, which was at Oregon Health Science University studying multiple sclerosis. So we would make these observations, and one of the things that we found was that people with multiple sclerosis experience fewer symptoms when pregnant. So we could ask a question: why does pregnancy alleviate symptoms of MS? And our hypothesis was pregnancy hormones alleviate MS symptoms. So the experiment would be to give a group of MS patients pregnancy hormones and observe what happens. And in our analysis, we would compare symptoms in pregnant, non-pregnant, and hormone-treated MS patients. And so this kind of process is, in general, it's a little bit simplified version of the scientific method, but it kind of gives you an overview of how we can systematically learn about the world. And because that's really what science is, it is a way of knowing. So what is chemistry then? It is the study of matter. And matter is anything that has mass and takes up space. So every object that you can see or experience or touch or feel, those things are matter. And mass is the measurement of the amount of matter in an object. On Earth, we tend to use mass and weight interchangeably. However, they are not the same thing. Mass is the amount of matter in an object. Weight requires gravity to act upon that object. So the weight is a measurement of the gravitational force acting on that object. And you could actually find the weight of several different masses on different planets if you want to go visit this website here. Like, for an example, a 50-kilogram object on Earth would weigh 110 pounds, and then on the moon that would weigh 42 pounds because the moon exerts about a sixth of the gravity that the Earth does. So the gravity pulling down on something is what weight really is. So if we want to talk about matter and the study of matter, the first thing we have to do is come up with a vocabulary and a classification system so that we can organize our thoughts and our observations and results. So we have two general categories of physical and chemical. So matter has physical properties and it also has chemical properties. The physical properties are those that can be observed without changing the composition. So that means that we have the size or shape or color or mass, those things, we can change these in general without affecting the actual chemical makeup of the product. Chemical properties describe how matter changes. So we're talking specifically about characteristics that describe how one compound would interact with another compound. So is something flammable? Does it burn readily? Is it an oxidizer? Does it make a flame hotter? How reactive is it? Those types of things are chemical properties. So we're going to use copper as an example. The physical properties of copper: density, melting point, boiling point, appearance. All of these things we can observe about copper without changing the fact that it's copper. So the appearance of copper is a reddish brown metal. It's actually kind of a pinkish color if it has no reaction with air. It's very bendable. It can conduct electricity. But the chemical properties of copper are that it reacts readily with oxygen. So in this example, we have our Statue of Liberty here, and it is pure copper. And then it is on Liberty Island in New York Harbor, which means that it is exposed to a lot of salty sea air that is very wet. And that reaction of oxygen in the air and the water and the sea salt and all of that kind of turns it this bluish green color. Now, a penny that is old will kind of be a dark brown instead of a bright pinkish red color, and that is a different kind of copper oxide. And so these are the chemical properties of copper that it reacts with oxygen to form this copper oxide. So we can classify these changes as physical or chemical. And so physical changes are those that they don't change the composition of matter, and we're usually talking about a physical property. So freezing point, and melting point or boiling point, these are all physical properties of water. And so freezing, melting, evaporation would be physical changes. Water itself, the chemical composition of water doesn't change if you have ice or if you have liquid water or if you have steam. Chemical changes occur when there's a change in the composition of matter. So if you burn some paper or you burn some wood in a fireplace, or copper reacts with air and water to form copper oxide, those are all chemical changes because the composition of the substance has actually changed. So we can further classify compounds that have the same physical and chemical properties throughout. These are substances, and we can have elements and compounds. So a substance that cannot be broken down into chemically simpler components is the element. So a balloon filled with helium is an example of an element. A substance like water, this compound water here has 2 hydrogen and an oxygen. So we could separate these hydrogens and this oxygen here. And so this would be a compound. The smallest part of an element that maintains the identity of the element is an atom. So gold, for example, if you have pure gold or pure copper or any pure metal, it is a collection of atoms of the same kind. So all of the gold atoms together make up these gold bars. If we have a compound that makes up a substance, here we would call this a molecule. So a water molecule and an ice cube have the same physical and chemical properties. They are both water, but the molecule is the smallest unit. And then these gold bars and a single gold atom would have the same properties. So we can further classify types of molecules by the number or the composition. So here we have how many atoms are in that molecule. So this is an example here of a diatomic molecule. It is a molecule because it could be broken down into a simpler component, right? This has 2 ends, and we could just have a single N all smashed together, or like all collected together. But we don't. We've got 2 of them, and so this is diatomic because there's 2 atoms. It doesn't matter that they're the same kind of atom. They are linked together like this. So this is the smallest unit we can have. So this counts as a diatomic molecule. Water here is an example of triatomic because it has 3 atoms, an O and 2 H's. And then polyatomic contains more than 3. So this sugar molecule here has lots of black carbon. White is illustrating hydrogen, and O, oxygen, is the red. And so again, it doesn't matter that these are the same, but because there are 2 of them, that's what you get: diatomic, triatomic, and polyatomic. Now, if we want to talk about the identity of those atoms, that's where we would talk about, is it homoatomic or heteroatomic? So in this example, nitrogen, N2, is a homoatomic diatomic molecule. Here we have a triatomic heteroatomic molecule. So we can also mix and combine substances. And so if you have 2 or more substances, that would be a mixture. And we can have multiple kinds. So we have heterogeneous mixtures and homogeneous mixtures. So a heterogeneous mixture is when you have an obvious combination of two or more substances. So if you have sand and water, or just mixed vegetables, or like a pizza or ranch dressing, those would all be heterogeneous mixtures. You can actually see the separation of the components. Whereas you have a uniform composition throughout, that's a homogeneous solution. So you can make a smoothie or some milk or coffee. Those are all homogeneous mixtures. They look the same throughout, but they have and it's a consistent uniform composition, but it's two different substances that are actually combined together. So we can also classify matter by the phase or the state. And so we have solids, liquids, and gases. Solids have a fixed shape and volume. It does not depend on the nature of the container. The solid itself has its own shape and volume. Liquids take on the shape of the container. They form a surface, but they have a fixed volume, whereas gases expand to fill a container. They don't have their own shape or their own volume. Later, we will talk a lot more about phase changes. But I just want to reiterate this because some students struggle with interpreting a phase change as a physical process, because we think about like liquids, solids, and gases as being so fundamentally different. But the physical properties of solid water, liquid water, and gaseous water are the same mostly. And so we don't need to chemically break down a molecule of water in order to observe the different phases. So you can have a liquid evaporate into a gas, and that gas condense down to a liquid, and this can go back and forth. There's no chemical change occurring here, so this is a physical change. These phase changes are all physical changes. So in this summary, this is how we can classify matter. We have a substance. So first off, is there only one substance present, or are there multiple substances present? So if there's only one present, then we either have an element or a compound. If there's multiple substances present, we have a mixture, and it's either homogeneous or heterogeneous. Then we can look at the phase. So as an example, let's take an ice cube. Ice, is it uniform throughout? Is there only one type of molecule present? Yes. So we come down here, we know water is H2O. There's two different elements in there, so it is a compound. And if we look at an ice cube, we see that it has definite volume and definite shape, and so it is a solid. And that is how we classify matter.